Hey everyone and welcome back to Prefusion. I'm Manish and today we'll start the lecture 2 of rectifiers chapter. So in this lecture we'll learn about half rectifiers with RE loads and we'll do few important questions on half rectifiers with RE loads. Okay, so in the previous lecture we did important questions. Before that we learned about half rectifiers with pure resistor and we did very good questions. If you haven't watched the previous lecture yet, you have to watch the previous lecture. Okay, now we'll start with this analysis of half wave rectifier with RE load. And first thing I want to specify here is that there's single phase half wave rectifier, right? These are also called one pulse converter. Why? Because I have told you that pulse number is 1 because in every period of 2 pi I am getting one single pulse, right? In a period of 2 pi I am getting a single pulse. That's why this is known as a one pulse converter as well. So half wave rectifiers are also called one pulse converter. Similarly, full wave rectifiers will be called two pulse converter because in a period of 2 pi there I will get two pulses. Once we'll do the analysis, there we'll see. So let's start with the analysis here, right? I will do both controlled and uncontrolled together, but for uncontrolled, right, what do you need to do? You need to make your Faraday angle of SCR alpha equals to alpha minimum. What is it? Alpha minimum. Alpha minimum will be theta. I will say what the theta value is just in a second. Okay, so basically you need to make alpha equals to alpha minimum equals to theta, and then your whatever analysis we have done, right, for controlled, it will get converted into uncontrolled. Basically this will be replaced with a diode. Okay, so we will repeat the same pattern. First of all, what do we mean by RE? RE is generally set for a battery, right? Like RE load means just a battery. Battery has its own resistance. This phone battery has its own resistance, and obviously it will have its own potential, right? And I am giving it some current so that the potential is increasing and the battery is charging. Okay, so that is basically what RE means. And here, right, first we will understand the period of forward blocking mode. Now can you just pause the video and say what will be the period of forward blocking mode? Just do the analysis by yourself and then tell me. Okay, so now I will draw the waveform of VT. What is VT? Basically when the current is 0, right, when the current is 0, when the SCR is off, then what is my VT? VT is equals to VS, only VS, no, right, not only VS, because VT has this drop as 0 because current is 0, E, right? On the cathode side of the thyristor I have E potential though, so VS minus E. So how will I determine the forward blocking mode? So basically, right, this will get shifted. Okay, if I draw a sinusoid, I'll just draw a sinusoid just real quick. Okay, draw a sinusoid. Just hold on, this will, if I draw it here, right? Yeah, here. So let me draw the sinusoid like this. Okay, now what is happening? This is VS, right? This is simply VS, but I have to subtract E as well. So if I just move this axis, so when VS is equals to E, then my VT will be 0, right? So at this angle, particular angle, let's name this as theta. This is the angle where, so VS at omega t equals to theta, it will be equals to E, right? And at this angle VT will be 0 because VT is VS minus E. So what will be this potential? This value, right? This value will be, this is the peak value of VS minus, I have to do the subtraction of E as well. So it will be VM minus E. So the maximum voltage that will come across the thyristor during forward blocking mode can be VM minus E. It cannot be more than that. It is not VM. Okay, it is not VM. And what is the maximum peak inverse voltage? If I observe here, the maximum peak inverse voltage, this is basically equals to what? Minus VM minus E. Okay, this is minus VM minus E, right? That is the maximum peak inverse voltage. Now what next we need to understand is that when is my SCR in the forward blocking region? So my SCR is in the forward blocking region here, right? So what is this value? If this is theta, then what will be this? If you know, right, our VS is equals to, at omega t equals to theta is E, and sine, right, the sine values repeat twice, once at theta, once at pi minus theta. So at omega t equals to pi minus theta as well, omega t equals to pi minus theta, this will repeat again, right? This will be also equals to E. Okay, so there are two cases here. So what will be this value? What will be this value? this value will be pi minus theta. Pi minus theta. Okay, so this value will be pi minus theta. Now if this value is pi minus theta, what can I say? So basically my SCR will be in the forward conduction mode or in the forward blocking mode in this region. SCR will be in the forward blocking mode. SCR will be in the forward blocking mode. Forward blocking mode in this region, right? Okay, so and it will be in the reverse blocking mode throughout this. So here, right, it will repeat here. Let's name this as theta as well. So this will be in the reverse blocking mode in this whole region. Okay. Yeah. Okay, no, this is not theta. Sorry, this is not theta. I'm sorry. This is 2 pi plus theta. Right. This point where this goes to 0 again. This is 2 pi plus theta. So this is in the reverse blocking mode. So what I can say is that what are the regions? So the forward blocking mode regions are this, right? So forward blocking mode region is between, like I am starting from theta and I am ending to 2 pi plus theta to take a complete cycle, else this is not symmetrical, right? That's why I am skipping before theta. So it is theta to pi minus theta. Okay, I cannot even go to until pi, and I cannot start from 0. I have to start from theta. So that is my forward blocking mode. What is my reverse blocking mode? Reverse blocking mode, okay, this will be 2 pi plus theta. Maximum can be 2 pi plus theta and minimum will be from pi minus theta. So one thing you have to understand is that now we are easily able to understand what is the forward blocking mode and reverse blocking mode, because there is no inductive component present. So because there is no inductive component present, so I can directly say about these regions. Whenever there will be inductance, all this analysis would be very difficult to make. Why? I will explain when we will study about those inductance, right? So what is the period basically? What is the period of reverse blocking mode? Period of reverse blocking mode is basically pi plus 2 theta, and forward blocking mode is basically pi minus 2 theta. Okay, so what value can my alpha lie between? So my alpha can lie between this value, right? Alpha can lie between this value only, because if alpha is some other value lower than this or higher than this, it won't turn on because it is in reverse blocking mode. My SCR can only turn on whenever it is in forward blocking mode. Okay, then only I can trigger. So what is the alpha minimum? Alpha minimum is theta. And what is this value of theta? If I want to compute this numerically, I have already computed it at theta, right? What is happening? Vs is equals to E. So theta will be sine inverse E by Vm. Okay, so this will be the value of theta and this will be the alpha minimum. And if I replace this with alpha minimum, if I replace my alpha with alpha minimum, it will simply be replaced with a diode. It will work like a diode, right? So my alpha can vary between this sine inverse E by Vm to pi minus theta, that is sine inverse E by Vm. Okay, so let's now start with the analysis. So I will divide this into cases. So I will start from theta and I will end to 2 pi plus theta, a whole cycle, because it is symmetrical. I will not start from 0. Okay, the reason is symmetricity. So now from theta to alpha, and my assumption is obviously alpha minimum, it is greater than alpha minimum, that is alpha has to be greater than theta, right? Or equals to. So from theta to alpha, what will happen? The SCR will be off. SCR will be off because it is in forward blocking mode. SCR is in forward blocking mode. Current will be 0. Current will be 0. SCR is in forward blocking mode. Okay, SCR is in forward blocking mode. So now what I can say is that current is 0, so and everything is in series. So IS will be equals to IT will be equals to IO will be equals to 0 amperes, and or VT will be simply equals to Vs minus E, and your VO will be equals to what? It will be 0. No, it won't be 0 because this drop is 0, but still I have E, right? So VO will be equals to simply E. Okay, and as I can observe that Vt is greater than 0, you can compute for yourself, because I will start from theta, right? I will not start from 0. It will be Vm sine theta, and sine theta I know it is equals to E, and as the omega t is increasing, it will only be more than this E. Hence my SCR will be in forward blocking mode. SCR will be in forward blocking mode. Okay, SCR will be in forward blocking mode. Okay, so let's now come to this case 2. Let's now come to this case 2. Case 2 is what? It is varying from alpha to pi minus theta, because after pi minus theta what will happen? After pi minus theta, natural commutation will happen. Okay, at this point natural commutation will happen because the supply will go like the Vt will go negative, and if Vt goes negative, natural commutation happens, right? Natural commutation happens. Okay, so at omega t equals to alpha, SCR gets turned on. So if SCR gets turned on, what will happen? This will be, SCR will be in SCR triggered, and if SCR is triggered, that means SCR is on, right? SCR is on. So we close the switch. Now what happens is my VO simply becomes VS, right? Directly connected across the supply, and my IS will be what? IS equals to IT. All of them will be same, equals to IO will be simply VO minus E by R, right? VO minus E by R, because what is the drop across the resistor? It is VO minus E, right? And that will be equals to my IS. Now can you tell me what will be the peak value of the current? IO max. Now it is a function of alpha, but there can be two values, right? One case is if my alpha is less than pi by 2. If my alpha is less than pi by 2, just like the previous case, my voltage will keep on increasing, until touch Vm sometime, right? So my peak current will be Vm minus E by R. Now this is for the case when my alpha is less than pi by 2. Okay, alpha is less than pi by 2. Just reduce the size of this. Okay. Now what is the other case? The other case is when my alpha is less than pi minus theta, obviously, but it is greater than pi by 2. Okay, it is greater than pi by 2. So if it is greater than pi by 2, what will happen? If it is greater than pi by 2, it will be like my maximum voltage that I can receive across my resistor, right? It will be Vm sine alpha, because after pi by 2, my sin theta is only reducing, right? So only whenever it is triggered, that will be the point where I will receive the maximum voltage. After that, my voltage will only keep on reducing. So it will be Vm sine alpha, just take this on the right hand side, minus E divided by R. Okay, so this will be the maximum current, IO max. Okay, so now what is the next thing? Next thing is, I forgot to mention one thing, that my E, right, in this computation of theta, theta has to be less than equals to pi by 2. If theta cannot be more than pi by 2. Why theta cannot be more than pi by 2? If theta is more than pi by 2, why? Because my E has to be less than equals to Vm. If my E is greater than Vm, what will happen? If my E is greater than Vm, right, this SCR will be never in the forward blocking mode. Why? Because the maximum value of this is what? Vm, and this is E. And if I subtract Vm with E, and I'm saying E is greater than Vm, then this will be some negative. Then SCR will never be in forward blocking mode, because this will always be less than that. Okay. Hence, for SCR to turn on, this condition needs to be satisfied. If this condition needs to be satisfied, that means at the edge case, right, when E is equals to Vm, what is the edge case? When E is equals to Vm. If E is equals to Vm, this becomes sin inverse 1, which is pi by 2. So maximum value of theta, if they ask you, the maximum value of theta can be theta max, can be pi by 2. It cannot be more than that, because else there is no point of having this converter, because this converter won't even turn on. So what's the point? What's the point of all this, right? If this converter never turns on and charges my battery. So that's why I forgot to mention the maximum value of theta can be this pi by 2, right? So let's now move on to the next case. I told you what is the maximum current, what is the current that I am getting, or what is the voltage that I am getting. Okay. So now let's go to the third case. This is the easier one. Is when it goes to pi minus theta. So I told you, right, it will go to natural commutation, because it will be in the reverse blocking mode. It will be in the reverse blocking mode. Okay, so if it is in the reverse blocking mode, what will happen is that my is equals to it equals to 0 because SCR is off, so it will be equals to IO, it will be 0 amperes. Okay, it will be 0 amperes. So my VO will be what? VO will be again E, right? It will be again E. Whenever this SCR is off, it is always equals to E. And what is my VT? VT is VS minus E, and I don't know, right? This Vs is always lower than E between pi minus theta to 2 pi by theta. So my Vt will be less than 0, hence it will be in the reverse blocking mode, and it will be in the natural commutation, right? It will be in the natural commutation. So these are the waveforms basically. So these are the waveforms, if you observe it carefully, that whenever up until this alpha 1, right? Up until this alpha 1, and I am assuming that my alpha 1 is greater than theta and lower than pi by 2. So the voltage, output voltage across the load will be E, and the current will be 0. If I have, okay, I haven't drawn the current, so current will be 0 basically, and the output voltage will be E. Then at alpha 1, right, alpha 1, what is happening is that suddenly the voltage is VO is equals to this Vm sin alpha. Okay, then this is equals to simply Vs. It follows the input. Then at pi minus theta, again the SCR will turn off, current will be 0, again the voltage will be E only, and the SCR will again start to block reverse voltage. SCR will start to block reverse voltage because SCR will be naturally commutated. So in this region, right, in this region, this region is known as the, okay, just hold on, this region, from 2 pi plus theta to pi minus theta, this region is known as the natural commutation period, and this region is known as the conduction period, right? Conduction period. Okay, this region is known as a conduction period. Okay, so these are the periods, and these are the waveforms if you observe here carefully. Now if alpha 2, right, alpha 2 is the edge case, where pi by 2. If I am observing at pi by 2, the voltage, okay, this will start from here, this will not start from down, this will start from here. Bit of mistake by my end. So yeah, let me just quickly do this. Okay, yeah, here it is correct. So you observe that up until before this alpha 2, right, it is equals to E, and just at alpha 2 it becomes equals to Vm only because alpha 2 is 90. Okay, so after this, right, the voltage is always reducing. So if I trigger at alpha 3, what will happen is that this will be Vm sin alpha 3, and this is the peak value. After this, voltage is reducing, so this will be the maximum value of current. This will be the point where I will receive the maximum value of current. After this, voltage is reducing, obviously current will also reduce, okay, as it is connected across a resistor. So these are the waveforms, these are the equations. So Is will be always VO minus E by R, alpha to alpha 3, or this, and these are the ranges. Okay, so I hope you understood the graph. I am observing that what is the peak inverse voltage? The peak inverse voltage will be this time Vm plus E. Why? Because if I just take the mod of this, right, if I just take the mod of the Vm is positive, E is positive, so it will be Vm plus E. This is the maximum amount of voltage that is coming across the diode in reverse blocking mode. In forward blocking mode, what can be the maximum voltage? It will be Vm minus E. Okay, that will be the maximum voltage that can come across the diode in the forward blocking mode. In this case, right, in this case, this will happen. In this case, where it is alpha 3, the maximum voltage it has to block in the forward blocking mode. Okay, so that all those things changes. So now, let's derive few things. That is the average output voltage. How do I derive average output voltage? Again think, what is my output voltage equals to, from theta to alpha, my output voltage will be simply E. Okay, I divided into 3 cases, right? So from theta to alpha, my output voltage will be E, that is constant. So that is simpler for me to compute. From alpha to pi minus theta, what is happening? From alpha to pi minus theta, it is my output voltage is directly equal to my input. It is following the input. So it will be Vs from here to here. Okay. Then from pi minus theta to 2 pi plus theta, right? Okay, this will be a bit wrong. This won't be 2 pi plus theta. Yeah, sorry. This will be 2 pi plus theta only. Okay, this will be 2 pi plus theta only because I am computing from theta. So from pi minus theta to 2 pi plus theta, this will be again constant E, right? Why? Because it is in the reverse conduction mode. So I have just done whatever I have analyzed in cases. So if we just write this, if we just compute this average voltage, so this will be what? This will be, again, this is again a single pulse converter because only I am receiving one pulse in over a period of 2 pi. Okay, that's why this is a single pulse converter. So now if I divide by 1 by 2 pi, this will be what? This will be E, and theta is in radians and alpha is also in radians. This will be alpha minus theta. Now what is this value? What is this value? This will be simply Vm cos alpha minus cos pi minus theta. Okay, plus this will be E into 2 pi minus 2 pi plus theta minus pi plus theta, right? So what will be this equals to? This will be equals to, I have already computed it, like if you computed it, what will be pi minus theta? Cos pi minus theta will be minus cos theta, so this will become plus cos theta and plus cos alpha. So your VO average will be simply 1 by 2 pi, this result, right? So if you add these two, what will happen is this theta will get cancelled and this will be alpha, and there is already a pi, so pi plus alpha plus theta. Okay, now for uncontrolled, right? For uncontrolled, what you do is you simply replace alpha equals to theta. If you replace alpha equals to theta, you will be able to receive the average output voltage expression. I will not take like you can remember this obviously, but if you are finding it difficult to remember, obviously always you can derive. Divide it into cases. What is happening from theta to alpha, right? My device is in forward blocking mode. Hence the current won't flow, but it is in forward blocking mode. So potential what will be the output potential? E. From alpha to pi minus theta, it will be in forward conduction mode, because from pi minus theta natural commutation will happen because the voltage across the SCR will be less than 0. Okay, so from pi minus from pi minus theta to pi 2 pi plus theta, okay, it will be in reverse blocking mode because voltage will always be negative. Now from 2 pi plus theta, the voltage will again start become positive, but I have already computed for a whole cycle. So that's how you can remember, that's how you can analyze this whole rectifier with RE load. Okay, half a rectifier. Now what will be the average current? Now this expression, right, VO equals to IO into R plus A. This expression is always valid. Now if this expression is always valid, then I can write, if I take the average of on both sides, this will be IO average will be equals to VO average minus E by R. Okay, so this will not be valid for RMS. This will not be valid for RMS. Why? Because if you apply the simple formula, right, if you do VO like 1 by 2 pi VO d omega t 0 to 2 pi. So this is what? This is VO average, and if I replace my VO with this will be, this is equals to what? This is, I will just write this. I will do this in rough to explain you why is this valid and why the RMS formula won't be valid. So this is VO average. Now I will replace my VO with what? I will replace my VO with this, right? I will replace my VO with this. So this will be IO into R plus E into d omega t. Now I can use I can break this integration down, right? If I break this integration down, so this will be 1 by 2 pi will be here, okay, and this will be, but R is a constant and I'm integrating from 0 to 2 pi IO, right? And if I divide by 2 pi, what will be this expression? This will be IO average and plus E d omega t. E is a constant, right? E is a constant, and I'm integrating it from 0 to 2 pi and dividing by 2 pi, so this will be E only. This will be E only. So what will happen is, I will just delete all this out. Okay, I'm just doing this in rough to explain you just in a quick second, right? So this will be equals to simply R into, so this thing, right, integrating IO from 0 to 2 pi divided by 2 pi, this is IO average, right? This is IO average, this is the expression for IO average plus E. So exactly this is what is written over here, right? So if I just replace, if I take this E on this left hand side and then divide by R, I will get this expression. So this will be valid. Okay, this will be valid, and I will always compute VO, and from there I will compute my IO average. I will not remember a separate formula for IO. I will not remember a separate formula for IO. I will just derive my IO average like this from VO. Okay, so I hope you understood how that IO average came up. Okay, so this is the average current to the side star. Now what about the RMS? What are the RMS? I will say don't remember, because they will never ask you RMS. Okay, they will never ask you the RMS voltage, trust me. Okay, because it's a very big formula, and to derive also it will take you huge amount of time. That won't be asked. Now you can obviously derive yourself, you can obviously derive anything, right? So but my recommendation is don't remember, this will not come in examination. Now why the same thing IORMS is not equals to VORMS minus E by R. Why is this not equal, but the average is equal? Why is it the case? This is because, I will just explain. just copy this. Okay. Why is this not equal? This is not equal because if I just write this, right? If I just write this thing here, that what is my VORMS? What is my VORMS? VORMS is what? 1 by 2 pi under root integrating from 0 to 2 pi VO whole square d omega t, right? And this will be totally under root of half. Okay, so what will be next? So if I want to replace my VO, so again I will replace my VO with the same thing that I replaced previously, right? I will replace my VO with this IO into R. So this will be, I will just evaluate this for now. I will just evaluate this for now. So this will be VOR, this will be IO into R plus E whole square. This will be equals to IO whole square R square plus E square plus 2 IO RE. Now due to this component, right? Due to this component, if you just apply the same methodology that I used previously, you will see that this term is extra. And if these two were supposed to be orthogonal, if IO and E were supposed to be orthogonal, then this equation would have been valid. But as IO and E are not orthogonal, we won't be able to write this in terms of IORMS equals to VORMS minus E. And I have told you, right, what is happening over here. Okay, so I hope you understand this. Due to this component, like you can, like I won't waste much time here because the lecture will go wrong. Due to this, everything is messing up. Okay, so you can derive and you can say like they are not equal. Okay, they are not equal, and the reason is this, because they are not orthogonal with each other. Okay, so okay, RMS output voltage I have computed. Let's go to the next parameters, that is for uncontrolled rectifier. I have told you, right? You just replace alpha with theta, and whatever VO average you will get, if you replace alpha with theta, right, you will get Vm by pi. Will this be Vm by pi? No, this won't be Vm by pi, right? This will be something different. I'm sorry for this. So I just copied this, but this won't be Vm by pi, right? So VO average we won't be able to compute. If I find out VO average, right, if I replace here with alpha equals theta, what will be this? This will be 2 Vm cos theta plus this will be pi plus 2 theta divided by 2 pi. Okay, so my average voltage will be this won't be the value actually. Average voltage will be 1 by 2 pi 2 Vm cos theta plus E into pi plus 2 theta. Like this pi plus 2 theta, why is it coming? This is coming because my SCR is not conducting for pi plus 2 theta period. It is the period for which SCR is not conducting. That's why my output voltage is directly equal to this. And this is coming to what? My SCR is connecting from theta to pi minus theta. That's why this component is coming. So I'm just simply adding the individual averages, and you can obviously compute ripples and all those things if they give you the VORMS, else you won't be able to compute. And VORMS we won't compute if they will give in the question. Okay, because that formula is very, very complex and we don't need that formula, trust me. Okay, so now what is the load power? Load power will be the power drop across the resistor and the drop across the power across the battery, right? Power across the battery. Now basically this is the AC power that I've already explained, right? How to write the power output power I've already explained in the first lecture. It will be IORMS into R because resistor can dissipate all components of power, but my battery, right, E potential can only dissipate DC. That's why this will be equals to E into IO average, DC to DC. Or if you want to compute by yourself, what you can do is, if you want to compute, right, the power E, what will be the power E? Power E will be 1 by 2 pi, okay, 0 to 2 pi, voltage into current, instantaneous power. Voltage is what? Voltage is always E, right? And what is power? This also I have explained in my first chapter, switches chapter also. Why is it DC, right? This also I have explained there. This is IO, voltage into current, into d omega t. Now E is a constant, right? E is a constant, so this will be E by 2 pi integration IO d omega t 0 to 2 pi. Now what is this? This is IO average, right? So that's why this IO average comes out to be like this. Power dissipated by the battery comes out to be this IO average. Okay, so this is the power dissipated at the load. What is the DC power? What is the DC power? the DC power dissipated at the load, right? DC power is simply equals to IO DC or IO average whole square into R plus E into IO average. So this also can be written like this, that if I take the IO average as common, this will be, just reduce the size a bit. IO average will be this. If I take IO average common, this will be IO average into R plus E. And do you know what this is? I just told you, right? What is this? This is simply equals to what? IO average into R plus E is, like if I take this R here and E is there, this is simply equals to VO average. So this, right, this I can write as, just make these things smaller because these are taking up too much space. So this will be simply equals to IO average into VO average. I told you, right, the DC will always be equals to IO average into VO average. This will be always equals to IO average into VO average. Now the interesting fact is, I will talk about another thing. What is my apparent power at the load? What is my apparent power? So my apparent power at the load, right? My apparent power at the load. What is apparent power? Apparent power is VORMS into IORMS. Okay. Now, if they ask you to find the efficiency of converter, you will write PODC upon PO, and this will be IO average square plus R into R plus E into IO average by plus E into IO average. This is the PDC, and this is the total power dissipated across the load. Now, what will happen is, many teachers, they tell you that this is like, they write the PODC like this. That it is the efficiency of converter is battery, how much power that the battery was able to absorb divided by total power, right? So sometimes if they don't specifically mention, although there is a bit controversy in this, okay, so if they don't specifically mention, you will write this PDC upon PO, which is this is always correct. Okay, now if they specifically mention what does the rectification efficiency mean or the converter efficiency means, they will mention that it is the battery power absorbed by the battery divided by PO, because mainly we are using it for charging of battery, and we will see how much power the battery can absorb, not the resistor, right? Because resistor is always dissipating. So this also, there is a controversy in this, there is a conflict of interest here, but sometimes they write the efficiency like this also, P battery upon PO. And what is P battery? P battery is E into IO average, and PO is already I have written over here, which is IORMS whole square into R plus E into IO average. Okay. Okay, P battery into P battery by PO is equals to EU into IO average divided by IORMS whole square plus E into IO average. Okay, so this is how you compute the efficiency. So there is a bit of conflict of interest. They will specifically mention which efficiency are they talking about. Now let's analyze the supply. We have analyzed the load side. We have analyzed the converter side. Supply voltage will always be same, right? It won't change. We have already established this at the lecture 0. Now, what about the supply current? Supply current will be simply equals to the load current, because it is a series circuit. So IS average will be equals to IO average, IS RMS will be equals to IO RMS. So you just remember one, VO average, and from that everything you will be able to derive. Everything else you will be able to derive with just simple brains. Okay, so that is the important part. Now let's take the analysis of supply, the power factor. So what is the power factor? Power factor is cos phi s PS upon SS. PS is equals to what? PO. If the converter is, assumption from here to here, the assumption is converter is ideal. If the converter is ideal, then obviously I can write PO equals to PS equals to PO. And what is PO? PO I have already derived. It is IO RMS whole square into R plus E into IO average. And what is SS? SS is simply the apparent power, that is VS RMS into IS RMS. And from there you can compute the power factor. Now what about the harmonic distortion? What is happening to total harmonic? So TSD for simple diode circuit with resistor I have already done in the prerequisites. Here, right, if you observe one thing is that what is my TSD? What is my TSD? My TSD is simply IHRMS upon IS1, right? TSD is simply IHRMS upon IS1. Now the harmonic components will obviously as the firing angle is increased, the TSD of the supply will increase further. So if I increase the if I increase the lambda, there will be more harmonic component in the current. Why? Because okay, where is the current waveform? Where is it? Where have I drawn the current from? I haven't drawn the current waveform, right? So what I will do, I'll just try to draw the current waveform real quick. Okay, just do this. Copy this. So what will happen is this omega t will get shifted, because at omega t equals to alpha 1 only, then current will be some finite value, that will be this time, right? What will happen is this will be Vm sin alpha minus E. Okay. Okay, how do I take this outside? This E will always be here. Okay. Minus E, right? This will be the value of current Vm sin alpha minus E. Okay, at this alpha 1. Now, like what will happen is, as the alpha is increasing more and more, what is happening? It is becoming less and less sinusoidal, right? This was still somewhat by sinusoidal, but as the alpha 1 is increasing more and more, the sinusoid, like the sinusoid portion is, like the current, supply current is less sinusoid. As it is less sinusoid, there will be more harmonics present at the output, sorry, at the supply end. Okay, so as the alpha is increased, the supply current will be less sinusoid, as seen from the waveform, less sinusoid. Hence, IH will increase more, and hence the TSD will be increased. Okay, so that's why. I hope you understood through the graph. I have tried to explain this intuitively. You can do this manually as well. You will check that the TSD is increasing. This is not VO. This is simply IO. This is not VO. Okay, this is the output current. So current is 0 from this up until 0 to alpha 1, and from pi minus theta to 2 pi plus alpha 1. Before that, it is equals to Vs minus E by R. Okay, so yeah, that's the thing about total harmonic distortion. So let's learn more parameters of our converter, that is the conduction period. What is the conduction period? Conduction period means the period for which it was on. It is basically omega t into t on equals to what? For what period it was on? It was on from alpha to pi minus theta. So if I just subtract these two, pi minus theta minus alpha, it will be on for this amount of period, that is pi minus theta minus alpha. That is exactly what I have written, divided by omega. That will give out to me in second. That will give out the time, as omega into t on will be give me the angle. Okay, so this is how we compute the conduction period. Then natural commutation period. Natural commutation period, I should just anyways write this, because that will be easier for you to understand. Now, what about the natural commutation period? The period for which the SR is reverse bias, reverse blocking mode. When it is in reverse blocking mode, from pi minus theta to 2 pi plus theta. From pi minus theta to 2 pi plus theta. So if I just do this, reverse blocking mode from pi minus theta to 2 pi plus theta. So it will be 2 pi minus theta. This will be pi plus this is 2 pi plus theta, right? Sorry, this is 2 pi plus theta. So this will be pi plus 2 zeta, and that is exactly what is written over here, right? So this is the commutation period. And what is the Vt max? That is the peak inverse voltage. That peak inverse voltage is Vm plus E. Okay, it is the magnitude of Vm plus E, and this is also operating in the first quadrant. That is in this case, right, my power will always be greater than 0. That is, the load always absorbs. Load always absorbs power. Okay, it never dissipates, it never supplies power, it always absorbs power. That is flow of the power, right? So we'll reduce this in size. So power always flows from source to load. Power flow is from source to load. It will never flows from load to source. When inactive load will be there, it will also flow from load to source as well. How we'll explain over there, don't worry. Okay, and obviously one thing is for sure, that one condition is there for all this to work, right? All these results to work, my E has to be less than Vm. E has to be less than Vm. Okay, so all this has to be satisfied, right? So like, what are a few drawbacks of this? So why do we don't use this in current scenario? So there is significant ripple components present out of the output. So this is still not pure DC, right? This is still not pure DC. The output current that I am observing, still not pure DC. This is not continuous, because continuous conduction is not present. It is 0 for a considerable amount of time. There is large harmonics present at the supply end as well. Ripples are present at the output and harmonics are present at the supply. You are not able to satisfy your best friend and your girlfriend. Okay, both things are going wrong. So obviously you have to do something else. You have to upgrade yourself, right? So good quality filters and harmonic reduction techniques need to be used in this rectifier, special rectifier, right? Typically that assures us we get constant current, but like we assume with this good quality filters we get constant current, but the load current is often discontinuous. That is, we don't get continuous conduction. Load current is 0, and that is not good for us, result in poor efficiency due to high ripple and harmonics. So this converter is like, we don't use this. We anyways don't use half wave now, we use full wave. But to understand full wave, we have to understand half wave. Okay, so these are the things that are drawbacks of this converter. Now let's start with few questions. So here, an ideal single phase half wave uncontrolled rectifier with supply 230 volt 50 hertz, the maximum voltage blocked by the diode is 425. Now diode can only block reverse voltage, cannot block forward voltage. So obviously this voltage, whatever they are saying, is the maximum voltage blocked in, it is the peak inverse voltage. And what is it in case of RE load? What is it? It is PIV, right? PIV we have already known, it is Vm plus E, right? Because in the reverse bias, the E will also be at the cathode of this diode. So it will be Vm plus E, and Vm will be what? Like your Vm will be 230. No, right? It will be 230, because this is whatever they said. If nothing is mentioned, this is RMS. This is not maximum. Do take care of this. So this will be maximum. So this will be 230 into root 2. 230 into root 2. And E, have they mentioned anything about E? Okay, they haven't mentioned anything about E. Okay, fine. Calculate the value of limiting resistor R to limit the DC current load to 10 amps. So basically my IO max, they are asking us, the IO max can only be 10 amps, right? IO max can only be 10 amp, or is it about the IO max? No, right? This is not IO max. Basically, what are they telling? They are telling us to limit the DC current of the load. To limit the DC current. DC current means what? DC current means IO average. So IO average should be equals to 10 amps or less than this. We limit this, so it will be equals to or less than 10 amps. Okay. So this is the current. Now we have to find out E. We can find out E from this, right? Because they have given us the 425 and Vm is 230 root 2. So from this information, I will be able to find out E. And how will I find out IO average? IO average will be this form, right? I will find out VO average, and from there I will find out IO average. Even if you don't remember, you can always derive. Okay. So E will be equals to here. We'll just quickly compute 425 minus 325. It will be almost equals to 100, because 230 root 3 is 325. So 100 volts. Okay. So I will use the formula here. So VO average will be what? VO average will be 2 Vm cos theta. Now what is cos theta? Cos, for that I need to find theta, right? So basically Vm sin theta will be equals to E, that I know. So theta will be equals to sin inverse E by Vm. So E is what, 100 divided by, so this will be equals to 17.90 degrees. Okay, so I can put all these values here. So what is the cos theta? So it is 0.951. So it will be 1 by 2 pi. Vm is 325 into 2 into 0.95157 plus E plus E into E is what? E is 100, right? E is 100 into pi plus 2 theta. Now theta is in degrees, so how will I compute it in radians? I will just multiply 17.9 into pi divided by 180, right? And obviously there is 2 as well, so degree will get cancelled, and I will be left with simply radians, 180. So into 2, okay, if I do multiply 2, this will be point, this will be equals to simply 0.625 almost. Okay, so if I just write all these things, right, if I just write all these things, this will be simply this. So what will be my VO average if I want to compute this VO average, right? So into 100 plus 325 into 2 into 0.95157 divided by 2 into pi. So this will be equals to, VO average will be equals to 10838, okay, 108,385 volts. Okay, this will be your VO average. Now what will be your R? So you know, right, IO average they have given me equals to 10, which should be equals to VO average, that is 108.385. okay, 385 minus, just hold on, I will check the calculation real quick, 1 second, if I am making a mistake or not. So this should be 325, where, like, let me just check it 1 second. This yeah, 125 is there. Okay, E is 100, fine. This is 425, this E is 100, yeah, 325 is there. 325 2 Vm upon cos, so into 2 into cos theta. So theta is 17.9. If I do the cos of that, if I do equate it, it is 618. So this value is 618. This value is 618, okay, 0.53. And how much is this value? So this is 17 point, this is pi plus 2 theta, right? Pi plus 2 theta. So 17.9 into pi divided by 180 into 2. And if I add this with pi plus pi, and if I multiply with 100, this becomes 376. This becomes 376. So this will be totally 376.64. Now if I just add these two, this will be plus 618.53 divided by 2 pi. So this will be 158. So I was making a mistake over there, that should be 158, right? This should be 158. That's why I was thinking that I'm making some calculation mistake. 158.38 volts. Now what will be the value? 158.38. okay, if I subtract it with 100, because it is VO average minus E divided by R, so R will be equals to minus 100 divided by 10, 5.83 or 85, you can say 5.85 ohms. Okay, so this will be the limiting resistance. So if I keep my resistance above this, obviously, IO average will be lower than something lower than this. That is fine. But my maximum value of IO average I have to limit within 10. Okay. If my is somewhat lower than this, my IO average will be increased because this value is constant. Right? So obviously this is the R has to be greater than or equals to. R has to be greater than or equals to. Okay. So this should be the value of the resistor. Now, what next? Now, like this is the answer to this question. This is the answer. This is the solution. This is the answer to this question. So R has to be R max equals to 5.85 ohms. So this is the answer. Let's solve another question. So this question is again similar type of question. An ideal single phase half wave control rectifier is shown in the below figure. The commutation time is 12.5 milliseconds. Calculate the battery charging current if the triggering angle is 60 degrees. So what do you mean by commutation time? So I have told you, right? Commutation time means the period for which it was reverse bias. What is the reverse bias period? It is reverse bias from pi minus theta to 2 pi plus theta. So basically this is pi plus 2 theta divided by omega. This is my commutation time is equals to 12.5 milliseconds. So what will be this equals to? So from here, right, if I compute the theta, so 12.5 means like this means, right, this means pi by 2 and pi by 2 and pi by 8. So pi by 2 plus pi by 8. How am I doing this? I will explain. Pi plus 2 theta equals to pi by 2 plus pi by 8. So this will become, if I subtract this with pi, okay, am I doing this something wrong? Okay, no, sorry. This will be pi plus pi by 4. Okay, so theta will be equals to simply pi by 8. So how did I compute this? So what you can do is, so here, right, basically like few numbers a electrical engineer should remember is that we work in 50 Hz, right? We work in 50 Hz. Most of the cases the frequency will 50 Hz, and if the frequency is 50 Hz, one half cycle will be what? Of 10 milliseconds. And in terms of omega t, if I multiply omega here, in terms of omega t, one half cycle is what? Pi radians, right? So this is 10 milliseconds plus 2.5 milliseconds. Okay, I know that 10 milliseconds is what? 10 milliseconds is half cycle, that is 10 milliseconds in radians for 50 Hz is pi. So what will be 2.5? It will be pi by 4, right? It will be pi by 4. So basically I just did that. I added a pi plus pi by 4 and I equated with this, right? I multiplied omega on both sides, and from there I was able to find out my theta. So this is a short trick, or else you can directly put here the omega equals to 2 pi f and this is pi, and you write this in terms of radians, right? You compute everything and you will be able to find out your answer. Okay, theta will be pi by 8, that is in angles 22.5 degrees. Okay, now you have found out your theta. What are they asking? They are asking us the battery charging current. So basically they are asking us to find the average current, right? This is the quantity they are asking us to find. For this, what values I need? I need VO average and E. Have they provided us E? No. I know R. So R is provided to me. I don't know VO average. I don't know E. So one thing I got theta. Now have they provided me VM? Yes, they have provided me VM. VM I know, but I don't know E, and I know alpha and I know theta. So how to find out E? So one thing I know is that my Vm sine theta will be equals to E. That is the basic formula that we derive, right? So from here I know theta, so I can easily find out my E. So it is basically equals to 325, because 230 root 2 is 325 into sine of 22. So 22.5 sine into, this is sine 22.5 degrees, 325. So this will be almost equals to 124. Okay, almost equals to 124.4 volts. This will be my E value. Okay, this will be my E value. So my E value is this. Now what next? I know E, I know R, I know theta, I know alpha. Alpha is what? Alpha is 60 degrees. given in the question, right? Given in the question, alpha is 60. Now just plug in all the values here, and you will be able to simply understand. You will be able to simply compute the value of VO average, and with the help of VO average, you will be able to compute the value of IO average. So what is this? It is 1 by 2 pi. You can derive, or you can always remember the formula. It is 1 by 2 pi 2 Vm, not 2 Vm, sorry, Vm into cos theta. So cos 22.5 plus cos alpha, which is cos 60, plus E into pi plus alpha plus theta, that is this I have to pi by 180 plus 60 plus 22.5. So this is the basic formula, right? This is the basic formula. So if I just compute everything, E is what? I can replace E with what? E is 124.4, and what is Vm? Vm is 325. Vm is 325. So this will be, I'll just compute everything here. So 22.5 cos plus 60 cos into Vm, that is 325. So this will be equals to this value, right? This value will be equals to 462.8, and this value will be what? 60 plus 22.5 into pi divided by 180 plus pi into 124.4. This value will be equals to almost 570. Okay, now if I add these two, right, this 462.8 divide by 2 times pi, this value comes out to be 164.36. so 164.36 volts. So this is my VO average. This is my VO average, right? So now what do I need? I simply need to compute the IO average, right? Simply need to compute the IO average. So IO average will be simply what? VO average, that is 164.36 minus E is 124.4 divided by R. This is the charging current. Charging current means the DC current. So I will say here specifically that the charging current, right? Battery charging current means how is the battery charging? It only charges to DC current, right? It doesn't charge to AC current. So battery charging current is the IO average or the DC current. Okay, so divide by R is what? R is 10, right? R is given, R is 10. So this, if I subtract with 124.4 divide by 10, this will be 4 ohms. So not 4, almost 4 amperes. So this is the answer to this question. So answer will be 4 amperes. This will be the battery charging current. Let's move on to the next question. So in the next question, a single phase like supply is given. AC supply feeds a step down transformer with 4:1 ratio. So this is a unique question because there is a transformer involved. So for the people, like the very basic concept of transformer is being used here. So even if you haven't studied machines, you will be able to understand, because in semester as well you study bit of machines, right? So it feeds a step down transformer 4:1. This supply feeds a step down transformer 4:1. The transformer is connected to an uncontrolled, so a diode half wave rectifier that charges a 120 volt DC battery. So my E is, this value is what? This is E. So you just write down the values, right? Through a series current limited ratio of 10 ohms. So R is 10 ohms. Okay, R is 10 ohms. Find the following charging current of the battery. So charging current of the battery means IO average. Okay, so we will go on to the next. So next is VO average. So obviously I will compute VO average first, then I will compute the IO average. Okay, so here first we have to visualize this. So there is a transformer which is a step down transformer 4:1. So if you know one thing, that this is the primary, this is a secondary, right? So what happens is the ratio of the voltages of the primary and secondary are with respect to their turns ratio 4:1. So if this side is 230 volts RMS, this side will be what? This side will be 230 by 4. Okay, and remember this is in RMS, right? This is in RMS. This is not the peak value. This is in RMS. So don't make this mistake, because this value, whatever they have given it me, is in RMS, not peak. Okay, so this will get reduced to 230/4. Now this is the this is the maximum voltage for this uncontrolled rectifier. So this is VM dash. I will write this as VM dash. Okay, so not VM. So if I want to write VM dash, I just need to multiply root 2 with it. This will be VM dash, right? So now from here I will be able to do the simple task. So now everything has been converted. This transformer is out of the picture. Only this is present. And why do we do this? I have like taught this in my prerequisites as well, that we do this to isolate the source of the load. Okay, because faults may happen, some problems may happen in the load that should not affect the supply side, and the fault in the supply side should not affect the load side. That's why to isolate we use transformers. Okay, in machines, in power systems we'll understand this more. So my new supply for the rectifier, right, Vs dash is simply equals to Vm dash sine omega t, which is 230 root 2 divided by 4 sine omega t. Okay, next is what I know. Vm, I know E is a sorry, this is a 120, right? This is not 12. Something has been gone wrong here. This should not be, okay, this should not be 120 actually. Mistake in the question. This should be 12 volts. Okay, this should be 12 volts battery. So this will be 12 because else this won't turn on. This won't turn, right? So this will be 12 volts. Now I know E. So what is VO average formula? What is VO average formula? VO average formula is simply this, right? Simply this. And you can derive this in seconds. For this I need to find theta. I need to find theta. So how do I find out theta? So I know Vm. I know Vm because Vm is Vm dash this time. I know alpha. Alpha is present. Alpha is this time theta minimum, right? Alpha is theta. Alpha is alpha minimum. That is theta. So it will be theta. So this will become 2 Vm cos theta. Okay. Next. So this will be pi plus 2 theta, because alpha minimum is theta this time. Okay, so basically what is theta? Theta will be simply sine inverse E upon Vm. So E is what? E is 12. Just hold on. Sine inverse 12 upon what is Vm? Vm is 230 root 2 divided by 4. So 4 will go above there, and I can simply find out the sine value. So 48 divided by 325. If I do the sine inverse, so my theta will be 8.49 493 degree, right? So theta is 8.493 degrees. So this is my theta. Now what will be my VO average? I have computed everything. So my VO average will be simply, I will just compute the things here. It will be 1 by 2 pi into this is what, 325 by 4. So this will be 325 by 2 into cos of 8.493 plus 12, just write this in the bottom, plus 12 into pi plus 2 into theta is what, 8.493 divided by 180. Okay, and there is obviously a pi. So what is this value? What is this value? So this value, right? If I do the cos of this and into 325 divided by 2, so this becomes 160.72. And what is this value? 12. Okay, just hold on. 8.493 into pi divided by 180 into 2 plus pi into 12. So this will be 41 41.256. Okay, this will be 41.256. Now if I just find out the VO average, VO average will be equals to plus what was this? This was 160.72. So 160.72 divided by 2 into pi. This will be equal to 32.14 volts. 32.14 volts. So this is the answer of the part B, and part A is what? IO average. So IO average is the battery charging current. It will be simpler only. It will be VO average minus E divided by R. So it is 32.14. Like that was a typo, that E was a typo, because if E is 120, obviously charging current will be negative, and that is not possible. 12 divided by R is what? R is 10, I believe. R is 10. So this will be almost equals to 2.214 amps. It will be almost equals to 2.214 amps. Okay, this will be the value of charging current. Now what is the peak inverse voltage? Peak inverse voltage, have I told you? No. Peak inverse voltage will be simply what? Peak inverse voltage will be simply Vm dash plus E. What is Vm dash? Vm dash is simply, if I just compute it, I've just computed it, still 325 divided by 4, so it is 81.25 plus this E is what? 12 volts. So this will be plus 12. This will be 93.25 volts. Okay, this will be the peak inverse voltage of the diode. Now what about the power delivered? So power delivered, right? So this was 1 2 3 4. Okay, this was like this. So this will be 2, this will be 1. So power delivered, right? Power delivered will be simply power delivered to the what? Power delivered to the battery. Remember, they have told us power delivered to the battery specifically. So battery means to this 12 volt battery. Resistor is there. This is a current limited resistor, but to the battery, how much power is delivered? So battery can only absorb DC power. Okay, battery can only absorb DC power. So this is the DC. So they are talking about the E into IO average. This is the value they are talking about. So this is E is what? 12 into IO average is what? 2.214. So this will be 2.214 into 12. So this will be almost equals to 26.6 watts. So this will be the answer of the last part. Okay, this is not the third actually. Sorry, this is not third. This is the fourth one, right? Fourth one. Okay, so this is basically all the solution of the question, whatever we learned, and we completely finished the RE part. And from the next part, we'll understand about inductance. So whenever inductance is present, the discussion becomes really interesting, and you won't be able to simply find out the forward blocking mode as we were finding out now. So there will be more complexity coming into the picture. So in the next lecture, we'll start with RL, RE load and all those things, right? So yeah, thank you for watching, and I will see you in the next lecture.